Even if you put the experiment inside of a lead box and you ground it, there's still a field that permeates through that
What
lead
evidence?
box. And there's even
That's the potential.
at the atomic level, we have elementary charges, dude.
The Cavendish experiment is performed perpendicular to gravity, so you don't have to worry about it.
We're trying to study gravity. What do you mean we haven't controlled for gravity? We're trying to study it.
You can't manipulate it. Even if you put the experiment inside of a lead box and ground it, there's no anti-gravity machine that you guys have ever created, as far as I know, to actually be able to manipulate the independent variable. Go ahead.
The Cavendish experiment is done perpendicular to gravity, so you don't have to worry about the downward force, and you manipulate the field by moving the masses closer in direction. So yes, you do manipulate the field.
That's fine. That doesn't negate my premise that there's still a field that permeates that lead box.
It doesn't matter because the gravitational force is downward and you're looking sideways, 90 degrees off. That's the brilliance of this experiment.
Can I share a paper with you guys?
That's true. We're looking at
yes, please.
Of electromagnetism on a quantum scale.
Oh, sure.
How it's a thing and the potential of fields.
QED is very well understood. Yeah.
Not by you.
No, I haven't taken any courses in quantum electrodynamics, but I've looked at a bit of quantum
Mine's
field
got
theory.
it right with the potential of the field. Just existing, just the potential. Not the influence, just the potential. Like, it's in your own works. It's in your own mainstream. And you're arguing against it. I don't get it.
This was written in
1959.
Oh, Aharonov and Bohm. Yeah, no, these guys are. Oh, is this going to be the Aharonov-Bohm effect?
Yeah. Japan, right? Japan's experiment, how they proved it real. They're like, holy shit.
So this is actually a really interesting. No, this is a really interesting example. I'm glad you found this because I've been thinking about these guys. So yeah, they made an experiment where you have this kind of flux tube of magnetic field, and it turns out Aharonov and Bohm wrote the theory on it. I don't actually know who made the experiment.
We're so far past that. They're doing it in modern times. Japan did it.
Yeah. Of course you would do it.
Right, yeah,
you can do it with light.
You know all this, right?
I'm gonna back out. I'm gonna make some coffee. I'm gonna make some coffee. Let me just say this. I'm gonna make some coffee. I'll back out. I just want to say this, and then Rigger, you can take over. My whole point here is that even if I grant you that the masses are attracting to each other, it's not mutually exclusive to GR, right? And there could be other forces at play that you guys aren't actually considering. Go ahead.
GR and gravity do not get along, but GR and gravity don't get along. We understand that. We're not talking about GR for the Cavendish experiment. We're talking about gravity. You understand there's a difference between these two?
Yeah, right. Gravity is the phenomenon that we observe. Right. Yeah, I mean, the Aharonov-Bohm effect is a really, really interesting part of quantum field theory. And it's also mathematically very interesting. But yeah, it basically suggests that. Sorry?
So can you say something?
Yes.
I'm just confused why you're holding the mic to just say nothing.
I'm sorry, did I like offend you? Okay,
No, you didn't offend me. I'm like, why? I'm just wondering, what are you stalling and wasting time for? You're just
trying to explain to you the Aharonov-Bohm effect.
I had to explain to you the paper from your mainstream. What are you talking about?
No, you didn't explain it to me. First of all, because I don't think you understand it. Because it's not a very simple effect.
When you didn't even know about it, right? And then act like, oh, this is very nice. I like this paper. It's very nice, soothing. It's great. It's this. It's that. The other thing.
I study physics, and this is specifically something that I was looking at with my advisor in condensed matter physics. The Aharonov-Bohm effect comes specifically
from. We talk about the influence, right, of the electromagnetic potentials. What does that mean to you?
The influence of the electromagnetic potentials on what specifically?
On the quantum scale.
Okay, so
what does that mean to you?
The electromagnetic potential on the quantum scale.
Paper makes you feel good. So could you explain it to me?
Yeah, I mean, the synopsis of this paper, though, actually, I couldn't tell you because I haven't read the entire paper, but the Aharonov-Bohm effect.
Really know about it. I didn't think you did.
No, this is the first time that I've seen the actual.
Trying to get to the bottom of it.
Okay.
To see if they're worth engaging with. Because I've read the paper. Okay. I know about the experiments in modern times that they're doing.
Have you ever calculated an integral?
Yeah. I probably don't. Right, NASA.
Probably don't. Yeah, I guarantee you don't understand that.
That make you feel better about your current situation of being.
Has to apply a force that has to do with mass. The more massive your body is, the stronger that tidal force will be, and ultimately you're going to have the thing collapse into a sphere.
It's inevitable. Right. Can't argue with you. In GR, it's a pseudo force.
In GR, it's a pseudo force. No, I mean it's a force, and it's a pseudo force in the sense that in GR we have this idea of what actual acceleration is. It's a very
Right.
It makes sense within the actual theory, but it's not. It's equivalent to think of it as a force. It just has to do with the fact that when you're under the influence of gravity, we consider that to be non-accelerating, while when you're not.
I get it. It has to do with the reference frames, but theoretically, right, according to GR, the masses in the Cavendish experiment, if it's truly due to gravity, they shouldn't be experiencing proper acceleration.
But I mean, they wouldn't be experiencing proper acceleration, but that doesn't mean that they're not accelerating in some other reference frame.
No, I'm not saying that they're not accelerating at all, right? Like you could say that in GR would be coordinate acceleration, but have you verified that? How confident are you that those masses aren't actually experiencing proper acceleration and could be picked up with an accelerometer? Because if that was the case, then you can't say it's gravity. It's not.
Well, I mean, how confident am I that they're not picking up that they're not experiencing proper acceleration?
Right. Because if that would be evidence for gravity, if you could put an accelerometer on the masses and that pick up any acceleration, then maybe you would have something. It still wouldn't be an experiment, but it would be evidence.
Well, in that case, you wouldn't be able to really. I mean, detecting the force from that would. The accelerometer itself is those two bodies attracting each other. That's your measure of acceleration there. I don't know. There's obviously a force generated, and we can see the effects of that force, and it's I mean it's pretty clear in every other stellar body.
We agree that
round.
We agree that it's. Well, I don't know about everybody in here, but most of us agree that it's an actual force. Newton considered it an actual force. Newton believed in absolute motion, absolute space, absolute time. Einstein did away with all of that, and he did away with causality. He says that gravity isn't an actual force. It's all due to reference frames.
He did not do
inertial and non-inertial reference frames.
Actually, Newton didn't have causality because gravity and Newtonian gravity is non-causal because it's action at a distance. It's instantaneous action at a distance. In GR, you have gravitational waves and things actually propagate, and that is specifically causal. Yeah.
No.
It's like built into the wave equation and all of that. Yeah. I mean, the entire idea is that things can't travel faster than the speed of light. That is relativity. So that is causality.
We're mixing up concepts, dude. Because Newton actually believed in a cause for what we call gravity. And he didn't believe in action.
Oh, that's what you meant by causality. Oh, I thought you meant causality in the other sense, like, things can't go faster than the speed of light.
Einstein brushed it off as nothing more than illusory observations, or like things that look like they're moving aren't actually moving towards you. It's all based off reference frames. So theoretically, the objects that are falling to the ground, they're not. The Earth could be moving up to the object. You don't know. There's no absolute reference frame. There's no preferred reference frame. Either or is valid in his model. And actually, when you put an accelerometer on a falling object, it doesn't measure any acceleration. You guys use that as evidence for it not being proper acceleration, but instead coordinate acceleration. So it's illusory. And due to the bending and warping of space-time, the curvature of space-time, things look like they're falling towards you, but they're not actually falling towards you.
I mean, and I think
it's worse than that line. It's an
appeal to paradoxical.
It's an appeal to paradoxical ideas that somehow is functional in reality. It's ridiculous.
I mean, incredulity isn't really do much there, but that's not even really the point.
Your snide remark has no relevance to what I said.
No, it's important that we distinguish between Newtonian and Einsteinian orbital mechanics, bro. It's because they're incompatible. Granted, you can reduce Einstein to Newtonian, but that's just a pragmatic fallacy. Just because you can use it and it works, because you have a conversion and it works, that doesn't mean that's reality, dude.
Well, I guess you could think about it this way: is that GR has predictions, and to the vast majority of things that it predicts, it gets right. Obviously, there are outliers, but vast majority of things that it predicts, it gets right. And so what it predicts is that when a body has enough mass, it will collapse in on itself and form this kind of spheroid. This is just what it predicts, and I mean that's also what we observe in things that have mass that have masses that we would expect them to have. Like it's a prediction. It matches observation. Kind of end of story. We have no reason to assume that wouldn't also apply to the Earth. And I think that's as simple as it is.
In order to have something, you have to possess it. So how does GR possess predictions?
Hey, Elijah, your mic is kind of bad, Elijah. I just stopped in to let you know. You need to be louder, Elijah.
All right. I don't think I can fix it in this environment. I'll just.
In your model, bro, the Earth has to experience acceleration, negative and positive acceleration.
What do you mean
around
the Earth?
when it's traveling around the sun, it actually has to accelerate ever so slightly and decelerate ever so slightly every single year. But that acceleration can't be picked up with accelerometers because according to Einstein, it's coordinate acceleration due to reference frames and due to the curvature of space-time. The Earth isn't actually accelerating or decelerating, even though our observations show it to do that, or the sun to do that.
Yeah, I mean, when you actually want to measure acceleration, then your proper acceleration is something different entirely. It has to do with how you experience that acceleration on your world line. The coordinate acceleration is tricky. It's not something that's very easy to understand. Even as someone who's kind of gone through it, so that might be something to think about. But I mean, yeah, the Earth does experience acceleration because it's moving in a circular path in that sense, like in the Newtonian sense. But what we call forces are kind of different. It's not exactly the same way that we call them in Newtonian mechanics.
All I'm saying is that our observations, right, show that the sun's actually moving around us. You guys say no, it's the Earth moving around the sun, right? And our observations show that the sun actually during its analemma, right, it accelerates and decelerates ever so slightly. And then you guys say, well, in order to make the heliocentric model work, Kepler had to come up with his 3 laws of orbital mechanics. I can't remember exactly. You got the asymmetrical orbit and the focal point, the foci, and then the I think it's the ellipse. He came up with ellipses.
So I mean, his laws have to do with how body, like the relationships between time and area swept out by specific curves and orbits. But yeah, that's beside the point.
So the Earth, if it's an ellipse, right, and it's not a perfect circle, it's not a perfect concentric circle, then it's necessary that it experiences acceleration, negative and positive acceleration, sort of like a track on a racetrack. I mean, a car on a racetrack. If you have an elliptical track, as it makes its way around the bend, it's going to experiencing. It's not only is it going to experience centrifugal forces and centripetal forces, it's going to experience acceleration and deceleration. Well, that's going to apply to the Earth too, even though we don't actually measure that on Earth, right? We observe it, but we don't measure it.
So what proper acceleration is talking about is specifically acceleration that is measured while on a geodesic trajectory. And in orbit, the Earth is kind of by definition in a geodesic trajectory, up to whatever debris it runs into. So it's not going to be experiencing its proper acceleration should be 0 in that sense. So yeah, gravity doesn't cause proper acceleration. But that's just because we've defined proper acceleration to be that way, because it's very nice to have when working with the Einstein field equations. When we're talking about, but I mean, that doesn't mean that it doesn't exist.
Well, we don't pick up any centrifugal forces or centripetal forces. Maybe a slight, you guys say because of the rotation, because of the rotation, maybe you might pick up a force, right? But you don't actually pick up a force when the Earth's moving around the sun, right? Even though it's an elliptical orbit.
You wouldn't expect to, though.
Yeah, because why?
Because if you actually calculate it, our actual trajectory, like across, wouldn't produce almost anything, because